Consciousness. Does the matter matter? Information and Complexity, Essay 1. Science comes in many flavours. There's physics, biology, chemistry, neuroscience, psychology, geology, astronomy, the list goes on and on. Each of these sciences has its own specialty, from uncovering the fundamental laws of the universe to studying complex human behaviours and social systems. Some sciences, I'm looking at you, physics, aim to uncover the basic rules that govern everything. Others focus on what we might call emergent properties, patterns and phenomena that we get from the interaction of simpler components. Think of how biology builds from chemistry, or how economics might build on principles of psychology. These special sciences, as philosopher Jerry Fodor calls them, each have their own methods, theories, and tools. And while they might not always call their subjects emergent properties, many don't like the term, but that's a discussion for another day, they all operate on one shared assumption. Physics is fundamental. Everything these special sciences study, from chemical reactions to social networks, ultimately happens in the physical world, following the laws of physics. If you're a physicalist, as most scientists are, this idea probably feels intuitive. According to the physicalists, everything we observe, from a lightning storm to a market crash, boils down to physical matter and energy interacting according to physical principles. And yet, this creates quite the puzzle. If the laws of physics can, in theory, explain everything, why do we need all these other sciences? Why do we turn to chemistry to understand molecules, biology to understand life, or psychology to explain human behaviour? What's left for these other sciences to discover if physics already covers everything? This is what I'm calling the puzzle of the special sciences. I've borrowed the term from Fodor's famous paper. It's not just a thorny puzzle about how science works. The answer to this puzzle has implications for how we think about complexity, reality, and even the possibility of artificial minds. To unravel this puzzle, we'll focus on 3 questions. 1. How do we typically try to resolve the puzzle of the special sciences? 2. What does it mean if the special sciences discover things that physics can't alone explain? And 3. What does the puzzle of the special sciences mean for consciousness? This essay kicks off a new series on information and complexity. It builds on ideas we've explored before, like reductionism and functionalism, and it raises new questions we started exploring in the little series about big questions. All right, let's jump in. Question 1. How do we typically resolve the puzzle of the special sciences? One common way to tackle this puzzle is by appealing to the concept of different levels of abstraction. This idea is quite simple. Sure, everything is ultimately made up of physical objects and events, but that doesn't mean the sciences are in conflict. They're just describing the same physical reality from different perspectives. We can think of it a bit like zooming in and out with a camera. A sociologist studying group dynamics, a psychologist examining individual behaviour, and a neuroscientist analysing brain activity are all looking at the same underlying reality. The sociologist might focus on how societal norms shape behaviour, while a psychologist might look at an individual's emotions. And the neuroscientist might measure the electrical signals in the brain that correlate with those emotions. Different zoom levels, the same scene. The same applies across the natural sciences. A biologist studying cells, a chemist looking at molecules, and a physicist probing atoms are all exploring physical systems, just at different scales. From this perspective, the special sciences don't discover new laws of nature. Instead, they provide more accessible ways to understand physical principles in context. At first glance, this seems like a tidy solution to our puzzle. All the sciences fit neatly together, with physics at the foundation, tying everything back to the same universal laws. But is it really that simple? Question 2. What does it mean if the special sciences discover things that physics can't? Think about a psychologist studying memory or an economist exploring markets. When the psychologist uncovers a new principle about how we recall memories, or the economist identifies a pattern in market behavior, what exactly are they discovering? Are they just describing physics in a different way, like zooming out to a broader perspective? Or are they finding something genuinely new, a principle or law about the world that physics alone could never reveal? This question pulls us into the long-standing debate between the reductionists and the non-reductionists. Reductionism is the idea that complex phenomena, like memories or markets, can ultimately be explained in terms of simpler components. A reductionist might say that memory will eventually be fully explained by neural activity, and market behavior will be reduced to the actions of individual agents. If you follow this view to its conclusion, all sciences will eventually point back to the same fundamental principles, the laws of physics, or perhaps mathematical laws. Non-reductionism, on the other hand, takes a very different view. It argues that some phenomena simply cannot be reduced to the fundamental. Memories, markets, and other complex systems may involve principles or patterns that emerge at higher levels of abstraction, which physics alone could never capture. This tension between reductionists and non-reductionists isn't just an abstract debate. It has major implications for how we do science and how we understand reality itself. To be scientifically meaningful, a concept needs to support valid generalizations. In other words, a scientific concept should allow us to identify principles or laws that apply across many instances and help us make reliable predictions. Let's take gravity as an example. Gravity isn't just a concept tied to a single event. It applies universally. Whether we're studying the fall of an apple, the orbit of a planet, or the motion of an entire galaxy, the concept of gravity gives us a framework for understanding all of this phenomena, and it lets us predict how objects will behave in different contexts. The law of gravity is a law that makes generalizable predictions. The key question here is whether the special sciences, like psychology or economics, discover concepts that meet this standard. Do they uncover valid scientific principles and laws that make generalizable predictions that physics alone could never fully describe? This would be the non-reductive view. Or are the concepts in the special sciences merely convenient shortcuts, tools we use to get a handle on extremely complex systems, but ultimately these concepts can be explained by physics? This would be the reductive view. This sounds all very abstract, so let's look at two examples to try to make this question more concrete. We'll look at money and the gemstone jade. The money example comes from philosopher Jerry Fodor, a champion of the non-reductive view, and the jade example is from philosopher Ye-Gwan Kim. Money. Economists like to study money. They like to uncover principles and patterns that make predictions about the effect money has on the economy. For example, one well-known principle is the quantity theory of money. This principle states that when there is more money circulating in an economy, prices tend to rise. Crucially, this principle holds true no matter what form money takes, whether the money is gold coins, paper bills, digital bits, or even seashells. Fodor points to this as a perfect example of why some concepts in the special sciences are irreducible. If we tried to define money in purely physical forms, we'd end up with what philosophers call a heterogeneous disjunction. Money is gold coins or paper bills or digital bits or seashells or whatever. Fudor isn't claiming that disjunctions can't be scientific. He's claiming that a list of things that vary wildly in their physical makeup couldn't possibly form a natural kind of thing, the type of thing we might study in physics. Despite the fact that money is, in physical terms, a disjunction, economics can formulate meaningful laws about money. The principles and laws generalize across money's different physical forms. Economics is able to do this because it recognizes money as something that is more than its physical forms. Money, it seems, is a scientifically meaningful term, even though to reduce it to its physical forms results in a disjunction. So, what about jade? What we call the gemstone jade is actually two entirely different minerals, jadeite and nephrite. Jadeite and nephrite, they look very similar, but they have very different physical properties. In other words, jadeite and nephrite form a disjunction. Observations about jadeite do not generalize to nephrite and vice versa. For example, if a geologist studied 1,000 pieces of jade and found that they were all green, but later discovered all her samples were actually jadeite, she couldn't say anything about the color of nephrite. We can't form meaningful principles and laws about jade that generalize across jadeite and nephrite. Let's return to our original question. Can the special sciences identify principles or laws that generalize and make reliable predictions? It seems that economics can identify such principles for money, but geology can't do the same for jade. Why not? The reason has a lot to do with multiple realizability. You may recall that something is multiply realizable if it can exist in many different forms while still fulfilling the same function in each form. For example, a toaster is multiply realizable. Toasters can come in many shapes and sizes, but all toasters serve the same function, to toast. Money is also multiply realizable. Gold coins, paper bills, digital bits, and seashells can all serve the same function as a medium of exchange in an economy. Jade, on the other hand, is not multiply realizable. While jadeite and nephrite can both function as gemstones, we don't define jade by its function. Instead, we define it by what it is made of. Things that are multiply realizable, like toasters and money, are defined by what it does. Things that are not multiply realizable, like jade, are often defined by what they are made of. A short side note before we move on. While I presented Kim's jade example as a contrast to Fudor's money example, it's worth noting that Kim uses the jade analogy to argue against Fudor. He questions whether multiply realized kinds, like toasters and money, can be proper scientific kinds at all. But let's not get into that debate just yet. Question 3. What does this mean for consciousness? In the introduction to this essay, I hinted that the puzzle of the special sciences might have implications for understanding consciousness. Functionalism, the idea that consciousness is defined by what it does, not by what it is made of, is currently the most popular theory of consciousness. It suggests that consciousness is more like money than like jade. Consciousness is multiply realizable. Just as money can exist as gold coins, paper bills, or digital bits, consciousness, according to functionalism, could theoretically be realized in human brains, alien biology, or artificial AI systems. The whole idea of functionalism hinges on whether consciousness is, in fact, multiply realizable. How confident can we be in this claim? What evidence supports the idea that consciousness is independent of its physical composition? When it comes to consciousness, does the matter really not matter? To try to get at this, let's return to Kim's jade example. Remember the geologist who collected 1,000 pieces of jade? She found that every single piece was green. From this, the geologist might declare all jade is green. But let's suppose that later we discover that the geologist only collected pieces of jadeite. None of the examples were nephrite. Nephrite, it turns out, is not always green. It can come in other colors too, like white or grey. What can we conclude? At best, we might confidently assert that all jadeite is green, but we have no basis to conclude that all jade is green, since the geologist didn't examine any nephrite. Her initial claim that all jade is green was wrong. She overgeneralized from incomplete data. This brings us back to functionalism's claim about consciousness. When functionalists argue that consciousness is multiply realizable, could they be making a similar mistake? Our understanding of consciousness comes almost entirely from studying biological systems, primarily humans, and to a lesser extent, other animals. If we only know of biological consciousness, can we confidently generalize to non-biological systems like AI or silicon-based life forms? Or are we overgeneralizing from incomplete data? Many believe we are inching closer to the development of artificial general intelligence, or AGI. With this possibility, we might want to ask, is consciousness more like money? Are we inching towards something functionally equivalent to human consciousness? Or is consciousness like jade? Are we inching closer to something that might merely imitate the outward appearance of consciousness, but actually be something entirely different? To sum up, I presented a dichotomy here. Consciousness is either like money or like jade. But of course, it's possible that consciousness is like neither. Consciousness has a way of resisting easy comparisons, which is part of what makes it such a fascinating puzzle. The idea of the special sciences raises all kinds of big questions that I didn't get time to get to in this essay. For example, what does it really mean for something to be an emergent property? How connected are our conscious experiences to the physical stuff we're made of? Is there something special about biology that gives rise to consciousness? And can we ever truly bridge the gap between physics and the messy, complex world of the mind? These are all things I'm looking forward to exploring in future essays. Next week. Earlier, I mentioned that functionalism is the popular kid right now. That wasn't always the case. Theories of consciousness go in and out of style, just like most other things. Next week, let's take a brief journey through history and explore how we got here. Why is functionalism so popular today? And where might the tide be turning next?